step away from using force of gravity because the force of gravity is not the only conservative force that's out there. There are other kinds of forces that behave like gravity. And so I want to just describe it as some generic force. Let's say you have an object and it travels along this path from A to B. There's multiple forces on it, okay? You can have all kinds of things pushing on it so that it travels in this path. But one of the forces that's acting on it is going to be a force that looks like this. It pushes on it pretty much in the direction towards B everywhere. So here it's pushing towards B, here's pushing towards B, here's pushing towards B. Okay. Not a component of the force, that single force in the midst of other forces. There are other forces acting on it to cause it to move along this path, but this particular force is always pushing on it in this direction. So what I'm doing is I'm demonstrating like when the object is here, it's pushing this way, when the object is here, when it's here, right? As it's going along this path, this one force is pushing like this. And we said that what makes a conservative force is a couple things. One is generally, it is only a function of position. So how strong that force is only depends on where it is at. And in this case, I'm kind of drawing them out to be all constant, like gravity. Okay? I'm modeling it like gravity, but I don't want to call it gravity because it could be. So at every spot, its positional change, the R, is changing. Maybe it's going a little more up, maybe it's going a little more sideways, this time it's going a little down, right? When we write dr, what we're saying is a infinitesimal change of position. And when we say f dot dr, we're saying at that particular instant, how much of my f is in the same direction as my change of position. Right? So sometimes it's not really in line with it, sometimes it's more in line with it. In this case, it's very much in line with it, something like that. Right? And what this interval is doing is it's adding up all the different components. Okay? So there's kind of three ways to influence how much work is done by this force. The strength of the force, right? So I can, if I had a dial, I could increase the strength of this, right? All of these can be long, but they can be strong, so they can get more work. You could change how far apart in B are. I could put B over here, or maybe add like a point C, and then it goes further, right? So the further I go, the more I'm adding up. Right? So I could increase the length, I have to do more work. I could change the angle, at least at any particular moment, that at this moment, this angle is different from this angle, is different from this angle. So if I'm adding up the little contribution, you know, how much does the force contribute to the work done at this moment depends on this angle. So it depends on kind of those three things. And when I add it all up, a conservative force will behave like this. There will be some function that can exist that is only a function of r, its position. Only a function of position. So that kind of take a look at the way this particular force is set up. How would this be different from if the object took a straight line distance? If it took a straight line distance so that the force was always in line with dr, then this would just be 1 and you would just have f dr. But the path would be short. And if you kind of think of it that way, since we're only ever taking the component that is parallel to each other, the more the angle is away, the less work is done by my force, the more the angle is in line with it, the more work is done by this force. And pretty much the way the math works out is that it doesn't actually even matter that it's turning away. Because in the end of the day, this still has to travel this much distance from A to B. If you kind of broke it down into like X components and Y components, sure it's going in the Y direction, but at the end of the day, its X position has to go from here to here. And the force F, if it points from here to here, will end up doing that much work no matter which way it goes. Because it can go way out of the way, but in other words, as it goes up and down, that's not related to what the work is done by this force. Let me give you an example like this. If I walk this way, I'm not going higher or lower, so gravity's not really doing any work on me as I go sideways, right? Gravity only does work on me if I fall or if I jump, right? It's only if I go up and down. So all my sideways motion doesn't influence my kinetic energy change due to gravity. That must be due to a different force. So it's the same idea here. This force is only related to any changes in position this way. It only does one of the unique things about this is that it doesn't matter what path you take. It can go up and down, it can go loop, it can even go out. It doesn't matter because from here to here it does positive work, and then from here to here it's going to do negative work, and it'll allocate to be the same. Doesn't matter. Here out here. Same thing. Doesn't matter. So, unique things about conservative forces. This only exists for conservative forces. In other words, only conservative forces have potential energy. Only conservative forces that behave like this, where it's only the position matters and the path that you take doesn't matter, have a equation that describes how it stores energy. Delta U is the change in potential energy, whatever it is, this one. So you could say gravity, you could say spring, you could say electricity, you could say R. Yep.
So only a conservative force can have a potential energy.
Yes.
So like if you're like pushing on a cable, the cable pushes back on you, that's a conservative force. The cable is storing the energy somewhere.
No, I would not consider normal force to be a conservative force. Because, think of an object going in a loop. The normal force is actually is not in the sense that the work that it does isn't like exchangeable or I'm trying to think of a good way to describe this. Just compare a normal force or like a tension force to the force of gravity. This force doesn't really depend on displacement, right? The normal force doesn't depend on where you are at. It depends on how fast you're going and how hard it has to push on you. It's not concerned. Your normal force is not a function of position here, so I wouldn't consider it a conservative force. What you're thinking of maybe is like if you stand on a trampoline and there's that normal force, but that's different. That's more than elasticity, right? That's a spring force that's you're storing. It is actually a function of displacement. I wouldn't really consider consider that a normal force the way we consider most other situations normal force. Okay? Like resting a book on the table or something. That's going to be an important point later on, distinguishing between conservative forces and non-conservative forces. So for now, let's look at a couple examples. The examples that we have for conservative forces, we have gravity, and we have the spring. For now, these are going to be the important ones that we'll use. And then later on, as we expand our models for different forces, we'll add them.
So should we memorize those? Should we memorize how to find them?
You should know how to find them, but you should memorize what they are. The goal. You don't really have to memorize all the chain rule stuff. That's not necessarily memorize.
Well, you're gonna learn anyway.
It's good to know. It's good to know. All right. I kind of want to erase some of this. Getting some space. So, shoot. I know I'm erasing stuff, even though. Oh, you're recording.
It's live.
So here's the thing. Why, what's the point of knowing that it's a conservative force? What's the point of knowing that there's a potential energy? It is kind of how we represent, or here, I'll put it this way. If this is true, if there's this negative u, which is a function of radius, is equal to f, which itself should be like a function of position, right? Dr. That means that I should be able to do it right at the other way around. That a change in potential energy over change in position should equal to what? Not quite. Let's go back for a second. Let's look at this. We said, let me bring back another one that may be familiar. We said that change in momentum equals to the integral of force times dt. And then we said that the change in momentum over change in time is equal to what? So if the integral of force with respect to time gives momentum, change in momentum, so that the derivative of momentum versus time is force, now I have the integral of force with respect to position is change in potential energy, so the derivative of potential energy with respect to position is force. It's not the force. It's not the change in force though. No. It's important to know it's not the change in force. This is the force at that position. Yeah. Yep. It does. So here's the thing. There is some math here that I don't think you even learned in Calc AB. So the dot product leading to scalar value is fine. I think that's easy to do. If your potential energy is a function of position, and you take the derivative with respect to r, technically, if you want to turn a scalar value into a vector, you use what's called a gradient. A gradient is something, I don't even know, do you guys learn that in Calc BC? I think it's multivariable calc. Okay, so a gradient is this. This is what you're looking for. It's this like upside down delta thing. What it's saying is it says take the derivative of u in the x direction, that's I. And then you take the derivative of u in the y direction, and that's your j. And you take the derivative of u in the z direction, that's your k. So if you look at what this essentially is the same as, this is like negative f of x plus the negative f of y dimensional vector. What it's saying is that you take it'll make a lot more sense in a second. Okay. This will make a lot more sense in a second. Let me just go back to this first product. Okay. Don't worry about the vector form yet. Just think of it in terms of where your U changes, in which direction it changes, is the opposite of the direction of your force. Okay. It will make a lot more sense in a second. Let's put it this way. Your force leads to a change in potential energy. That's what this says. If you have no change in potential energy in a certain direction, you have no force in that direction. Which actually means that your force is always perpendicular. Just kidding, I'm skipping ahead a little bit. Let me go back. Sorry. So if your force always leads to a change in potential energy, then perpendicular to your force should be a line where you have no change in potential energy, right? Because your force always leads to potential energy, so perpendicular to it, you should have no change in potential energy. In this direction, perpendicular to F, right? So, at least as far as F is concerned. Yeah, as far as F is concerned. So, if F was the only force here, there'd be, in regards to this kind of potential energy, there's no change in this direction. So, if this happened to be like 30 joules of potential energy, along this line, everywhere along this line is 30 joules of potential energy. And so we call this an equal potential line. Or an equal potential surface slash line. Imagine it's dimensions. Right? So, here, I'll give you an example, a perfect example of an equal potential surface. Has anyone played Wii golf? Oh, yeah. Nice. Right? You try to swing it, and then the guy's like, right? You're like, no, I just flipped the wrist, and he's like, in Wii Golf, there is a option where you can turn on the contours of the map. So if you look at contours, are like contours on maps. What are contours on maps? Bumps. Not exactly bumps.
Like the elevation, exactly where the elevation is in different things.
Right. So it shows elevation. It shows that if I have something like this, and then we have something like this, and then maybe there's like something like that, right? What it shows is everywhere along that line is supposed to be at the same height. Right? So this might be 500 feet, 600 feet, 700 feet. Well, if they're all at the same height, they should have all the same potential energy, gravitational potential energy, right? So that's kind of what this is showing. This is like a contour line. And in Wii Golf, they show the contour lines by changing color. It was like the deeper it is, the darker the green, and the higher it is, the lighter the green. So anywhere with the same color is supposed to be an equal potential surface or line. The reason why I say it's a surface is because technically, this could be like a hill that's sloping up. So if you go along perpendicular to the contour lines, you're going uphill. But if you imagine there was a slice through the mountain, there's a surface there that is all at 600 feet. That's a surface, right? If you just slice the whole mountain, there's a slice, a cross section, right? Or like a tree stump. That is one equal potential surface. Okay, so that means that F is always perpendicular to equal potential surfaces. So your force always pushes in a way where you decrease potential energy. So if my force is this way, this might be a line where it's at 10 joules. And you can have everything in between. Maybe it's equal potential line here of 20 joules, and then equal potential line here of like 25 joules or something like that. You have decreasing potential energy this way. And what's very useful about looking at it this way is an object here traveling to here loses the same amount of potential energy as an object going from here traveling to here. It's the same potential energy. If it's this, from here taking this round path, we'll lose the same potential energy as just taking a straight path. Or taking like a whatever path. Doesn't matter. If it starts here and ends here, it must lose 5 joules.
So it'll lose just 5. It'll lose 5
Delta U.
but it could be.
You can have all sorts of other
Another
forces.
one, you can have
Yes.
spring force also against.
Yes, absolutely.
gravity
So, if I take a pendulum, not a pendulum, what was Shahir? What was that one? Oh, no, here, I'll just use this. Okay. Now, I don't want a pendulum, I want a spring. This is an interchange of gravitational potential energy and elastic energy, right? I have two forces going on where it's both gaining or losing gravitational potential energy, gaining it, losing it, gaining it, and my spring or my elastic potential energy is also kind of has something going on. And they interchange. What we'll see later is that they interchange in a very simple way. It's linear. You just add it up, which makes it really nice. You just say, okay, you have spring potential energy minus from potential energy plus, and then whatever other force is going on, and then all of that, when you find a network, gives that kind of exchange. So then what it means is that this will gain the same amount of kinetic energy as this object going from here. 5 joules of gravitation, not gravitation, but 5 joules of potential energy transform here, just the same as it transforms here. So it doesn't matter how it moves. If it goes from here to here, potential energy change will be 20 joules. It'll be 20 joules of kinetic energy, and then you do 1/2 mv squared, and you get your velocity out of that. In other words, they'll have the same velocities no matter what path they take, if it's a conservative. Yeah, so when you look at gravity, it's the same thing. In terms of its vertical velocity, you gain just as much velocity this way as it gains this way. In terms of up and down, the velocity changes the same. Okay, so if F is always perpendicular to potential surfaces, that means that if this is a contour map of these potential lines, I put an object right here, the direction it wants to go is always going to be perpendicular to the surface, to the line. It should always be perpendicular. Which means that equal potential surfaces can be a really useful way of figuring out where something wants to go, without necessarily having to draw forces everywhere. You don't necessarily want to know, you guys have to do slope fields, right? You don't necessarily want to do slope fields everywhere. But if you can create these potential, equal potential surfaces, sometimes they're easier to model or create than forms. Okay, so something like right here, like that, perpendicular. Okay. The other thing that's interesting about this, let's say at 700 feet, this is, 50 joules, and this is 30 joules. That means that from here to here is a 20 joule loss, right? This is a change in 20 joules, which is the same as this, which is also a change in 20 joules. They both are a change in 20 joules.
the dot product between force and dr be greater? Because the dr would be more in the direction of force.
They shouldn't be greater, because they should equal the same change. It's the same change, 20 joules, 20 joules.
Dr is more in the direction of force.
You have a more what?
More in the direction of force.
You have more force. If this is less, then this must be more. Or alternatively, you have to change more potential energy in a shorter distance. Joules is newtons per second. Oh, no, sorry. Newtons meters. Sorry, newton meters. Joules is newton meters. Well, I guess if it were like that's curved, right? But it doesn't necessarily have to be straight. This is shorter. This is longer. This is straighter. This is more curved. This is the same. No, because the force is always perpendicular to the equal. That's the most important. It has to be perpendicular. The force. This is the force. This is you. This is you. This is you. F is what's actually causing it to move. So it's gonna want to move perpendicular. Yeah. You can't just draw a straight line distance because that's not perpendicular. It doesn't want to move that way. Maybe another way to think about it too is I've only drawn a few potential surfaces, but you can imagine that there's an infinite number of potential surfaces that could fit. It's like a gradient. We'll get to that. Well, it has to match this amount. So maybe in here, it could whatever, but yeah, once it hits that point, it's perfect. At least the force is perfect. Okay, so let me go back a little bit since someone has. How do you turn a scalar value to a vector value? The change in U and the change in R has a specific direction. In this case, it's like this. So, if you were to have a map of your potential energy as a function of all positions, x, y, z. So not just U. Well, it's like U as a function of position, right? So you have U of x. You guys remember? You guys are right? You can describe in all three-dimensional space, if that was possible, at every position, U as a function of x, y, z, right? So like maybe it's 60 joules here, then 30 joules and 40 joules, and maybe it goes from like 60 to 50 to 40 to 30, but in this direction it's just like 60 to 60. Right? So imagine these are like sheets going up. So there is no rate of change in the x direction. So you have no rate of change in the y direction. So you only have a j component for that. Right? So you add the change in that direction. That's how you create a gradient. A gradient is you take a scale, you take a map of just a quantity, like let's say density. Right? Density has no direction to it. And you look at the ocean water, and you look at density, usually you have increasing density as you go down. So you have an increasing gradient of density downwards and up, sideways. Right? But if you look at, I don't know, there's all sorts of different things you can do with gradients. Like temperature is a big thing. When you look at the temperature of like solid body metal, you want to know how it's if you can map the temperature at every location, then you can look at the direction the heat travels, because the heat travels across equal potential temperatures. So you have an equal potential surface of temperature of 100 degrees. The heat's gonna want to go from 100 degrees, 90 degrees, 80 degrees, and then you have a temperature. You have a temperature gradient, and then you look at how temperature changes in those directions. I mean, this you do not have to know whatsoever. So you guys haven't seen this in DC either, right? Who's Shahir? Arjun, did you ever take BC? Yeah, yeah. Did you guys do gradients?
No.
No. Alright. Then you won't. I don't think you'll get to this until you do multivariate. It's usually counterintuitive. So I think you're essentially doing calculus right now. Facebook make some linear algebra. I don't know. But, so you'll get to that later on. Yeah, mixed with random. Okay, so any questions as to how conservative forces work? So a conservative force behaves in this manner. You can lay out these equal potential surfaces so that the conservative force always wants to push down these potential energy surfaces. Gravity. Gravity is the easiest one. In real life, or not in real life, on a bigger scale, okay, not just at the surface of the Earth, but if you take the Earth really far away, gravity pulls inward according to an inverse square law. Gravity is G capital M little m over r squared. In other words, the further away you are, the weaker the gravity. So if you double the distance you are away, you get more strength of gravity. And so you can look at, there is a gravitational potential energy. Looks like that. And it's interesting to look at why it's negative. I'll explain that later. But basically, you can look at these concentric spheres of equal potential surfaces that you leave here. And the graph of it is kind of like this. So as you go further and further away, you're leaving a gravitational well. You actually have a negative potential energy here on the Earth that you're stuck in. It takes energy to get you out of the Earth's gravitational pull. So it takes energy to get yourself not negative away from Earth. It's kind of an interesting way to think about it. So that's one example of these equal potential surfaces. One of the things that I did in grad school was, if you look at an asteroid, how do you figure out the gravity from an asteroid? We look at the Earth and we assume that it's a sphere. It's not, it's oblong, which means that it's not technically actually a perfect model to say that you have gravity is a perfect sphere. You don't have concentric spheres of gravitational potential energy. So if you have an asteroid and you look at the gravity of an asteroid, then it looks like a potato. And you look at, okay, well, there's more gravity here than there was gravity here or something. So then you suddenly have these gravitational potential energy kind of shapes that are interesting. How do you calculate that? How do you model that? It's pretty intense. One of the craziest things actually I saw was, especially with Earth, there are parts of Earth you don't have a uniform distribution of mass around the surface of the Earth. So there are sections of Earth that are slightly higher mass or higher gravitational pull. And one way to model it is with waves. You do a Fourier series sum of waves of mass around the Earth, and you add them all up, and then you have this model of like how Earth mass is distributed. It's a really weird way of thinking about it. Okay, so we got about 7 minutes left. Couple last things. So, how do we use certain forces? It all comes down to this. work. And then the concept. We can break work by forces acting on an object into two kinds of work. You have conservative work and you have non-conservative work. So if an object is experiencing different forces, some of those forces are conservative, some of those are not conservative. It's binary, conservative or not. Conservative work or conservative forces can be represented with a potential energy. K is kinetic. So you can do work, or sorry, when you do work with a conservative force, you can model it with some sort of potential energy function, which we'll kind of classify it out. Kind of like what we did with forces, potential energy function, but this is like a special kind of conservative force that can be represented this way. Your non-conservative work can be represented in two kinds of forces. You have dissipative work, or dissipative forces, and you have external forces. External forces is kind of just a grab bag term, just everything else. Everything that is not these. So external forces tend to be like tension, normal force, stuff like that. You push on it with your hand, whatever. Right? That's external forces. Dissipative forces tend to be forces that always oppose the direction of motion. Friction always opposes the direction of motion. Drag always opposes the direction of motion. If you're moving this way, the force is that way. So that means that these forces always do negative work. They will always do negative work. They will always take work out. They will always work against the moving object. And then all of this will lead to a change in kinetic energy. So, usually, external forces are forces that we apply. We apply tension, we apply normal force, we push on things, whatever. So, that's kind of how we influence. And if I take these two and I add it to the other side, what it tells us is essentially the conservation of like mechanical energy here is when you do work on an object, either speed it up, or you will store it, or it will be lost. It's going to be one of those